Welcome to Scigest, your fortnightly science from the Bioeconomy Science Institute.
Kia ora, and welcome to Scigest. Today we're going to chat to Peter Bell about biofouling, what it is, and what we can do about it. Peter is a research technologist here at our Nelson site. After completing his master's degree looking at culturing, he went on to do some hydrology work in Australia and also here in New Zealand before he returned to marine sciences here at Planet Food. He's been heavily involved in the Precision Seafood Harvesting Project, the Reimagining Aquaculture program that we recently talked to Susie Black about, and a variety of other projects with direct applications to industry. So welcome to Scigest, and thanks for joining us, Pete.
Thanks, Julie. It's my pleasure to be here. My privilege to speak on the behalf of the wider team to undertaking this work. So, thanks for the opportunity.
I guess we should probably start with a definition of biofouling, because that's probably not a term that everyone's familiar with. So maybe you can start us off with what is it and why do we care?
So biofouling is basically the community of organisms that grow on any structure placed, in this context, in the ocean, looking at marine biofouling. So it sort of starts off in a successional process. In the first few minutes, we'll get sort of proteins and various things sticking to the object. And then beyond there, we get colonisation by bacteria, fungi, etc. And then that slowly builds to eukaryotes and builds right up to all mussels and seaweeds and things like that. So there's a whole range of organisms that will change seasonally, temporally, spatially. So we get a real different community throughout the year in different locations. They can be affected by what the material is and what might be growing around them, whether they're on a fish farm or just a floating structure at sea. So they pose a number of problems for us. So the primary one that most people probably be familiar with is biosecurity. So they can act as a vector through shipping and transportation of fouled materials between countries or between regions. And then more specifically for aquaculture, we're looking at drag, damage. There's a lot of weight as it grows, density, especially shelled organisms like barnacles, mussels, etc. And then we have a loss of buoyancy or waves, currents will deform structures, cause damage, and potentially loss of farms in the worst case scenario, famous case in Canada. And then within that matrix we can also have it act as a vector for disease, pathogens for either the farmed organisms or for humans, food safety. And we can also get animal welfare issues, so either through the occlusion of water flow that will stop or slow the oxygenation of cages, or we will get during cleaning or say storm events, disruption of organisms like cnidarians, so hydroids and anemones, and these release stinging cells into the water which can cause physical damage to gills and skin, which then will either affect the health and well-being of the fish or degrade the value of that harvest. There's a lot of different tiers, a lot of different sort of pressures, and a range of different species that we're dealing with within these communities.
Yeah, that sounds like a pretty big, meaty problem there that you've got your teeth into.
Yeah, fantastically interesting space to deal with, sort of an ecological dream in some ways, because you are looking at so many different pathways and different actors within that. The good thing for us is that we can probably filter that down to some of the bad actors, and that's where the research sort of comes in to help us direct downstream solutions towards those elements that are causing the biggest issues for us as researchers, as wider aquaculture industry in New Zealand.
And do you think that's quite comparable to some of the, challenges that are faced on land in, for example, the horticulture industry?
Yeah, so what we're looking at is probably a more complex community in some senses, because we're working in that three-dimensional space. We've got the constant supply of gametes and things. I'm sure that horticulture would face those same issues, but the pressures in the medium are probably exacerbated. So what we're hopefully able to do as we get a better handle on the communities and the structures and the changes throughout time is to maybe leverage and utilise some of the knowledge within that horticulture space they've been doing for a long time, building up the integrated pest management strategies, because there isn't a silver bullet. vast amounts of money spent on addressing biofouling, either for shipping or aquaculture annually, either just in the management or research to improve responses. And there are some effective solutions, but they don't form a full picture. So we're going to have to find elements that work together and to look at the timing of interventions, and a big pressure to move away from those toxic or questionable strategies that have been used in the past. So there's a lot to be learned there. We're not trying to reinvent the wheel with our research. We're sort of looking at just changing some tyres here and using the tools. So that starts with that knowledge of what's growing where and when is the fundamental for us. And there's some reasonable literature out there, but it's patchy in terms of what it's telling us in those finer scale patterns that we need to expose to be able to target effectively. Like I say, the worst actors within this. If you look at an orchard, they would monitor for pest species using pheromone traps. They would then look at their thresholds of detection and then spray or undertake their intervention at that point. So we are a reasonably long way away from that in terms of some or many species. So we need that fundamental understanding before we can tailor and time those interventions to sort of get the best outcome for industry.
Would you like to go into some of those current management practices or the best ways that people deal with biofouling at the moment?
Yeah, so traditionally people might be familiar with coatings. So a really famous historical one is tributyl tin, which is very effective anti-foul in terms of toxicity, especially to invertebrates. But research found that it was accumulating in sediments and then causing issues for the development of invertebrates in heavily contaminated areas like ports and harbours. So you had changes to sex determination in snails, for example, and affecting populations there. So that's now, I think, been banned globally. There's a few small areas where it's still used, I believe, but on a large scale it's been banned. And the next one is copper and zinc, or next ones. Copper and zinc, and they function a similar way. Copper is toxic because of the blood of invertebrates, so they use a copper-based blood generally, and probably other biological pathways as well. That's been phased out in New Zealand and Australia in terms of aquaculture. They used it to coat nets, and it's still used elsewhere in the world, but with problems or concerns around bioaccumulation, etc. That generally isn't used by the industry at the moment. So the main solution currently is cleaning, which is undertaken using sort of remote control water blasting systems of various types. These have large wheels, they're lowered down or driven around on the inside of the nets, and they use generally higher pressure water streams to dislodge and blast away growth. Some use brushes, some use lower water pressure, and that generally happens during peak growth about every 10 to 14 days, sometimes a little bit more often. That is generally reasonably effective at keeping the mesh clean, but releases that material into the water around your fish and into the surrounding environment. So there are some concerns around that having wider ecological animal welfare issues, and some of the companies developing those machines are looking at ways to recover or have ways of recovering that biomass, which is done in some situations, but not as a standard solution to date. Dealing with that biomass downstream still has issues, and that's where some of the research is coming in here at Plant and Food, is to look at how we might utilise that biomass, add value, and then create an incentive to retain and recover that biomass. And that's some of the research around when organisms are occurring, or where and when, for recovery and sort of optimising those processes. So there's different strategies that haven't been explored in great detail, and that's part of the wider program that we're undertaking here to examine some of those potential pathways.
What's the downstream plans for the underwater vacuumed up biofouling?
Yeah, so that fits into our wider program here under the Growing Futures funding stream. So we have a program called New Open Ocean Ecosystems, with a view that as aquaculture moves further offshore, it's going to create new environments and habitats for fouling organisms. And they will bring new challenges that the industry kind of hasn't addressed or come across to date. So we're looking at the wider issue and how we might approach that from a BSI perspective. And there were sort of 4 research aims that came out of that. One is the one that I'm leading around characterisations. We need a standard set of tools that allows us to understand what's in the fouling matrix, when and where. And doing that using sort of emerging technologies. We want to leverage genetic metabarcoding to look for those cryptic species that are hard to see visually and that often cause sort of disproportionate effects. So that's where you have your pathogens, your parasites, your disease-causing organisms. So they're pretty critical to capture. And then visually, so we want to look at the eukaryotes, the large organisms, the ones that cause the occlusion to the mesh, that cause the drag and density issues. So we're kind of using those technologies to try and build standard tools that allow us to examine these questions going forward and support both internally research and also ultimately industry to make some really good decisions. And then research aim 2 is looking at modulation suppression. So led by Dan Colleen, they've done some amazing work in terms of plant-based coatings that look like they're having an impact on fouling growth and may prove to be suitable coatings for industry with more testing. So that's a really exciting option to replace some of these toxic traditional compounds that are used, and with the right application can support industry to either exclude fouling from areas that are maybe hard to clean or potentially particularly critical, slow down growth to give more time between cleaning. There's a range of advantages that they would provide and a lot of interest in that space. And then Research Aim 3, led by Matt Cumming, is looking at a utilisation. So what is within the fouling biomass that, if recovered, could we turn it into various products or raw materials for other industries? So they're doing some really interesting work around the components within biofouling communities that could be used to make more environmentally friendly foams, etc., which is fantastic. We've got a biomass that grows very quickly without inputs and is interacted with anyway, so finding a pathway to then recover that may provide additional income for farmers at a more regular interval than sort of a fish production cycle of 2 or 3 years, and may offset some of those operating costs, especially around cleaning, which would be sort of a win-win. And you'd be removing that material from the environment, so you'd be reducing that footprint as well. And then finally we had a research aim looking at a herbivorous omnivorous fish, butterfish, mararai, which lives around New Zealand's coastal rocky reefs and feeds as adults in particular on large brown kelp. But during their juvenile stage and probably through into adulthood as well, they do browse on the small invertebrates and other algae. So as a candidate for potentially co-culture to help keep cages clean, sort of an exciting opportunity there. And that's now moved into its standalone research, looking at the husbandry and maintenance of that species. We'll hopefully still be doing the biofouling work to some degree, examining sort of their browsing preferences within fouling sort of matrices. So that's a really exciting part of the work still to come.
Yeah, it sounds like a really big, ambitious set of research aims, but maybe we can dive a little bit more into the one that you're leading with looking at the biofouling and how it sort of progresses. So do you maybe want to talk about what that settlement system looks like that you can test this with?
Yeah, so luckily growing biofouling generally, apart from a couple of instances, is pretty straightforward. So we put structures in the water, as I said, and things settle and grow. So the main issue is then putting that through analytical pathways. So if we were to to take the materials commonly used in aquaculture. Mesh, it's sort of soft and pliable, so if we then try and remove that from where it's been deployed, that will deform or disturb the organisms living on it, and then we'll be disrupting sort of that community. So at the very base of our system is a frame that holds the materials of interest. It's a dual frame system, so we have a small frame that carries the material, and most of our work so far has been on mesh and fabrics, some of which are used, say, in the reimagining program, which allows really nice collaboration between some of the work streams here. And then that fits within a larger, more robust frame because it's got to be able to survive in the ocean. So traditionally people have used, say, PVC pipe glued together, but that will often degrade and break under stress. So we have used a plastic plywood product and then designed the frame using Ross Jacobs here, one of the engineering staff, that's CNC routed, so a local plastics company can make these in bulk for us. And that then attaches to a mooring line and allows us to deploy that pretty much anywhere for the growing period, which is typically for a community to mature is about 4 to 6 weeks, where you're starting to get really heavy settlement of the eukaryotes, and etc. So it's a nice standard frame system, really light, easily deployable from small vessels, and we can have serial numbers, etc. etched into those frames too to track them through the process, and lots of replication, repeatability, so we can test different materials, different coatings, etc., which is pretty critical for this work. Those frames then will be able to be taken, and we've developed an integrated imaging rig, so we can put the frame, which has 6 smaller squares within it, into the rig, and then using just cell phones and waterproof housings, we can take high definition standard images that then feed through into our machine learning tools that we've been developing with the help of David Ashton here, in terms of analysing the occlusion. So we use a blue background and then look at the occlusion values to look at that aspect for operators, and then we're developing community models to look at what the composition of those communities are. And then following the imagery, we can take that sample and preserve it, generally frozen, and extract the DNA signatures for the metabarcoding of bacteria, eukaryotes, diatoms, etc., which PhD student in the program, Tian's been doing for her thesis. And that allows us to take the imagery and put that aside the genetic component, and we can see what we can see, and then also assess what we can't see within that microbiota. And over time, as we get a better understanding of those relationships, it should create new opportunities to sort of explore that data further and look at those relationships for maybe predictor species or different settlement patterns at different times of year, what's driving those patterns within the communities. And we've already seen that in Tasman Bay, at some of our offshore sites, a very strong seasonal difference. This has been noted elsewhere with biofouling, but by capturing that within the system, we can start to see how understanding these seasonal changes can help managers maybe make different intervention decisions. One of the issues with cleaning, for example, is it's thought to potentially select for more robust species, and in the case of hydroids, they're a particularly problematic species for aquaculture, but they have kind of a rhizome root system similar to some ferns. So by cleaning, there's a thought that potentially you're just cropping those species, and if you're selecting for them, they may persist beyond their natural cycle. So making some different decisions around those interventions may help extend the time between cleaning interventions, which will reduce the cost of cleaning and potentially disruption to fish and things. So I think the granularity for aquaculture is really going to be really important going forward, and emulating what we see in horticulture, where these broad brush, say a pesticide application has now been much more targeted, and that saves the producer both time and money in terms of repeated applications, but also in terms of sort of food safety stand downs, all those great outcomes.
It sounds like you've already really learned a lot, especially about seasonality with this sort of combined computer vision and genetic species identification, but are there other differences in sites or areas where you've deployed these structures and these methods that you've noticed?
Yeah, so that's one of the interesting things. For Town's thesis, we looked at sheltered sites within Pelorus Sound and the Marlborough Sounds complex, a traditional farming area for mussels and salmon, and then, like I said, the Tasman Bay sites, to try and look at the effects of exposure in particular because of the likely push of aquaculture further offshore for a variety of reasons: space, social licence, dispersion of wastes, etc. There's definitely a move further offshore. So we want to understand what those communities will look like and the challenges that they will present. We may face less pressure from algae or other species which aren't traditionally found at those sites, at least initially, but it may be dominated by things like barnacles or species with longer-lived propagills. So they might present different challenges in terms of drag and density, especially when you're looking at novel enclosures or novel systems, say submerging systems, etc. Understanding those shifts in community and developing tools to sort of give farmers options to work with them are really critical. And what we may also see is over time those communities shift as those facilities are established and communities settle and expand over time. They're likely to feed propagills. So the communities will constantly change, and we're also seeing potentially shifts in marine communities as part of climate change as well. There's sort of a focus on developing resilience in horticulture. We're seeing those effects on our finfish production already, but there may be these underlying shifts of, say, fouling communities where farmers will have to adapt and change. And then also the ever-present biosecurity component as well. So understanding these communities is critical from a range of issues, but really challenging, like most research activity in the marine environment. That's another reason for keeping the costs down, standardising the tools and making them accessible to potentially operators. So rather than researchers going out to collect the data, if we can find a way of making these processes easy and straightforward while maintaining quality and consistency, that may be a way we can source and partner with industry to give us those finer scale insights we need to develop the solutions that are possible.
I think we've talked quite a bit about some of the solutions that exist or might exist in the near future for biofouling and how to deal with it, but what does your ideal biofouling management program look like?
Ideally would be great to see a balance, so really targeted use of effective natural suppression strategies where they're needed, but also really exploring how we could utilise this biomass. There's a lot of potential pathways that it could support. You looking at the expansion of sort of biofuels, biogas, fertilisers. There used to be a massive transfer of marine productivity to New Zealand's land via seabirds in centuries past. With the loss of those, we've lost that pathway. Is there a way we can re-establish the movement of those nutrients back through the system? Carbon sequestration pathways, high value extracts. You sort of look at an aquaculture production system. This is the original integrated multi-trophic aquaculture, if you like. It's sort of the holy grail amongst many researchers in the aquaculture space, and it's already doing it. So how do we utilise that? How do we leverage what exists? There's no inputs. It's more consistency and sort of quality will be the main barriers. So I think if we can emulate horticulture and really getting to grips with an integrated biofouling management system, it's been proposed by other researchers in New Zealand, then we'd be a long way to making our aquaculture industry more resilient, both operationally, financially, and potentially diversify those outcomes as well, which would just be fantastic. It's a missing piece in New Zealand's sort of economic prosperity, and there's a huge potential there, given that the scale of our marine estate, to utilise that, but doing so in sort of maintaining those sustainable outcomes. And I think if we get in early and work down that sort of roadmap, down that pathway, partnering with industry, then there's some good outcomes possible, and we can use horticulture as kind of the blueprint for doing that, I think.
Sounds like a really cool, optimistic future where you might be sitting on a biofuel-powered flight eating some farmed fish wrapped in some biofouling seaweed, maybe?
Maybe, yeah. I mean, it's quite exciting for me with more of an ecological background, working with the chemists here and understanding those insights, what is possible. I think that it's been a great collaborative exercise to look at the skill sets that we have and apply it to a really challenging, novel area. And I think that it's set up a really good roadmap for future work, either within BSI or hopefully collaborating across industry and across researchers here and elsewhere. It's a universal wicked problem, biofouling, but there's huge potential there for us to make some real world differences by understanding the beast in more detail. And for me, that's really exciting. The ocean is such a blank canvas with a lot of these systems. So to be exploring those is a real privilege and a real exciting place to be. And hopefully as we gain more understanding and production out there, then more resources will flow to do this work.
Yeah, and what's been the most surprising thing you've learned so far in this journey?
I think it's really opened my eyes to the tools that are coming down the track. I think that the move towards ecosystem-based management is really exciting, and the tools are now emerging through meta-barcoding, machine learning, AI analytical pathways and engines to start getting to grips with that, and that's got just massive potential across both aquaculture and wild capture in the marine space. We've got a bright future. New Zealand's a maritime country, and everyone has an investment to some degree or another in the marine space. So that delivering, the best outcomes for all of us is a really exciting space to be in, and to see those tools develop to achieve that is fantastic. It's sort of got quite a one-size-fits-all approach at times, and to sort of find scale solutions that work, and to see aquaculture and other activities working alongside healthy ecosystems and healthy fisheries, etc. That's a really exciting end goal for this space.
Ooh. And apart from surprising things, what are you most excited about for the future?
I guess one thing that hasn't surprised me so much, because I worked with power and I've worked in marine education, etc. So the marine critters excite me, and what they do. When you see a scallop swim when a starfish approaches, or a power get up and slide off when a starfish, a predator, approaches, or starfish, it's called Stignasta inflatus, and it stands up on the points of its arms and forms like a little tent or a cave, and then drops down when invertebrates crawl underneath it. Or you see a nudibranch that eats the stinging cells of hydroids or anemones, and then incorporates that into defensive packets on its back. The marine environment's always full of amazing creatures, but the biofouling sort of represents that on another level, when they're all packed in together, sort of fighting for space and interacting. So I think when you have a look at fouling and it's seething with life, and you see, for example, a skeleton shrimp, they look a bit like the advertising inflatable waving arms, advertising sort of
Like a pizza shop or something.
Yeah. Holding on with sort of a ring of feet at the bottom, and the females have a little brood pouch of eggs, like a little basketball on their abdomen. That seeing some of these new creatures, some of these really interesting beasties, is always exciting to me. Yeah, seeing little nudibranchs eating the hydroids, or egg masses from different organisms, and things coming and going, layering, worms living in underneath. It's a really interesting microcosm to deal with. So that's been an exciting part of it for me, is to see these crazy critters and hopefully be able to show others that it's not just brown sludge that's a problem, but there's actually multiple layers and a whole world within these coatings. So that's cool. I like that. And potentially maybe, as BSI comes together, there's going to be more opportunities to collaborate across and into those ecological spaces and into those community-focused research streams that to date haven't been as high a priority for us. So yeah, exciting future ahead.
Yeah. Thanks so much for joining us today, Pete, and for this deep dive into biofouling. And thank you all out there for listening today. I hope you'll agree with Pete and me now that this really isn't just brown sludge. Don't forget to subscribe and rate us on whichever podcast channel you're tuning in on, and if you learn something new, please share this with a friend. Mā te wā, until next time.